are centered on the origin, we can try to fit a line to it. To do this, we start by drawing a random line that goes through the origin. Then we rotate the line until it fits the data as well as it can, given that it has to go through the origin. Ultimately, this line fits best. But I'm getting ahead of myself. First, we need to talk about how PCA decides if a fit is good or not. So let's go back to the original random line that goes through the origin. To quantify how good this line fits the data, PCA projects the data onto it. And then it can either measure the distances from the data to the line and try to find the line that minimizes those distances, or it can try to find the line that maximizes the distances from the projected points to the origin. If those options don't seem equivalent to you, we can build intuition by looking at how these distances shrink when the line fits better, while these distances get larger when the line fits better. Now, to understand what is going on in a mathematical way, let's just consider one data point. This point is fixed, and so is its distance from the origin. In other words, the distance from the point to the origin doesn't change when the red dotted line rotates. When we project the point onto the line, we get a right angle between the black dotted line and the red dotted line. That means that if we label the sides like this, A, B, and C, then we can use the Pythagorean theorem to show how B and C are inversely related. Since A, and thus A squared, doesn't change, if B gets bigger, then C must get smaller. Likewise, if C gets bigger, then B must get smaller. Thus, or maximize the distance from the such a fuss about this, and calculate C, the distance from the projected point to the origin, square. So, for this line, PCA projects the data onto it, and then measures the distance from this point to the origin. Let's call it D sub 1. Note, I'm going to keep track of the distances we measure up here. And then PCA measures the distance from this point to the origin. We'll call that D2. Then it measures D3, D4, D5, and D6. Here are all 6 distances that we measured. The next thing we do is square all of them. The distances are squared so that negative values don't cancel out positive values. Then we sum up all these squared distances. And that equals the sum of the squared distances. For short, we'll call this SS distances, or sum of squared distances. Now we rotate the line, project the data onto the line, and then sum up the squared, and ultimately, we end up with this line. This line is called Principal Component 1, or PC1 for short. PC1 has a slope of 0.25. In other words, for every 4 units that we go out along the gene 1 axis, we go up 1 unit along the gene 2 axis. That means that the data are mostly spread out along the gene 1 axis, and only a little bit spread out along the gene 2 axis. One way to think about PC1 is in terms of a cocktail recipe. To make PC1, mix 4 parts gene 1 with 1 part gene 2. Pour over ice and serve. The ratio of gene 1 to gene 2 tells you that gene 1 is more important when it comes to describing how the data are spread out. Oh no, terminology alert! Mathematicians call this cocktail recipe a linear combination of genes 1 and 2. I mention this because when someone says PC1 is a linear combination of variables, this is what they're talking about. It's no big deal. The recipe for PC1, going over 4 and up 1, gets us to this point. We can solve for the length of the red line using the Pythagorean theorem. The old a squared equals b squared plus c squared. Plugging in the numbers gives us a equals 4.12. So the length of the red line is 4.12. When you do PCA with SVD, the recipe for PC1 is scaled so that this length equals 1. All we have to do to scale the triangle so that the red line is 1 unit long is to divide each side by 4.12. For those of you keeping score, here's the math worked out that shows that all for the old a squared length of the equals b squared plus 0.12. So the length of the red line D, the recipe for PC1 is scaled so that this length equals 1. All we have to do to scale the triangle so that the 2. For those of you keeping score, here's the math worked out that shows that all we need to do is divide all 3 sides by 4.12. Here are the scaled values. The new values change our recipe, but the ratio is the same. We still use 4 times as much gene 1 as gene 2. So now we are back to looking at the data, the best fitting line, and the unit vector that we just calculated. Oh no, another terminology alert. This 1 unit long vector, consisting of 0.97 parts gene 1 and 0.242 parts gene 2, is called the singular vector, or the eigenvector for PC1. And the proportions of each gene are called loading scores. Also, while I'm at it, PCA calls the sums of squares of the distances for the best fit line the eigenvalue for PC1. And the square root of the eigenvalue for PC1 is called the singular value for PC1. Bam! That's a lot of term value for the square, the eigenvalue for PC1. And the square root of the eigenvalue for PC1 is called the singular value for PC1. Bam! That's a lot of terminology. The eigenvalue for P is called the singular vector, or the eigenvector for PC1. And the proportions of each gene are called loading scores. Also, while I'm at it, PCA calls the sums of squares of the distances for the best fit line are called loading scores. Also, while I'm at it, PCA calls the sums of squares of the distances for the best fit line the eigenvalue for PC1. And the square root of the eigenvalue for PC1 is called the singular value for PC1. Bam! That's a lot of terminology. Now that we've got PC1 all figured out, let's work on PC2. Because this is only a two-dimensional graph, PC2 is simply the line through the origin that is perpendicular to PC1, without any further optimization that has to be done. And this means that the recipe for PC2 is -1 parts gene 1 to 4 parts gene 2. If we scale everything so that we get a unit vector, the recipe is -0.242 parts gene 1 and 0.97 parts gene 2. This is the singular vector for PC2, or the eigenvector for PC2. These are the loading scores for PC2. They tell us that in terms of how the values are projected onto PC2, gene 2 is 4 times as important as gene 1. Lastly, the eigenvalue for PC2 is the sum of squares of the distances between the projected points scores for PC2. They tell us that in terms of how the values are projected onto PC2, gene 2 is 4 times as important as gene 1. Lastly, the eigenvalue for PC2 is the sum of squares of the distances between the projected points and the origin. Hooray! We've worked out PC1 and PC2. To draw the final PCA plot, we simply rotate everything so that PC1 is horizontal. Then we use the projected points to find where the samples go in the PCA plot. For example, these projected points correspond to sample 6. So sample 6 goes here. Sample 2 goes here. And sample 1 goes here, etc. Double bam! That's how PCA is done using singular value decomposition. Okay, one last thing before we dive into one last position. Okay, that's how PCA is done using singular value decomposition. Okay, one last thing before we dive into a slightly more complicated example. Remember the eigenvalues? We got those by projecting the data onto the principal components, measuring the distances to the origin, then squaring and adding them together. We can convert them into variation around the origin by dividing by the sample size minus 1. For the sake of this example, imagine that the variation for PC1 equals 15 and the variation for PC2 equals 3. That means that the total variation around both PCs is 15 plus 3, means the variable by the sample size minus 1. For the sake of this example, the total variation, and that means PC1 accounts for 15 divided by 18 equals 0.83, or 83% of the total variation around the PCs. PC2 accounts for 3 divided by 18 equals 17% of the total variation around the PCs. Oh no, another terminology alert. A scree plot is a graphical representation of the percentages of variation that each PC accounts for. We'll talk more about scree plots later. Bam! Okay, now let's quickly go through a slightly more complicated example. PCA with 3 variables, in this case that means 3 genes, is pretty much the same as 2 variables. You center the data. You then find the best fitting line that goes through the origin. Just like before, the best fitting line is PC1. But the recipe for PC1 now has 3 ingredients. In this case, gene 3 is the most important ingredient for PC1. You then find PC2, the next best fitting line, given that it goes through the origin and is perpendicular to PC1. Here's the recipe for PC2. In this case, gene 1 is the most important ingredient for PC2. Lastly, we find PC3, the best fitting line that goes through the origin and is perpendicular to PC1 and PC2. If we had more genes, we just keep on finding more and more principal components by adding perpendicular lines and rotating them. In theory, there is 1 per gene or variable, but in practice, the number of PCs is either the number of variables or the number of samples, whichever is smaller. If this is confusing, don't sweat it. It's not super important, and I'm going to make a separate video on this topic in the next week. Once you have all the principal components figured out, you can use the eigenvalues, i.e., the sums of squares of the distances, to determine the proportion of variation that each PC accounts for. In this case, PC1 accounts for 79% of the variation. PC2 accounts for 15% of the variation, and PC3 accounts for 6% of the variation. Here's the scree plot. PC1 and PC2 account for the vast majority of the variation. That means that a 2D graph using just PC1 and PC2 would be a good approximation of this 3D graph, since it would account for 94% of the variation in the data. To convert the 3D graph into a 2-dimensional PCA graph, we just strip away everything but the data and PC1 and PC2. Then project the samples onto PC1 and PC2. Then we rotate so that PC1 is horizontal and PC2 is vertical. This just makes it easier to look at. Since these projected points correspond to sample 4, this is where sample 4 goes in our new PCA plot. C2 is vertical onto PC1, PC2. Strip the 4% of the variation in the data. To convert the 3D graph into a 2-dimensional PCA graph, we just strip away everything but the data and PC1 and PC2. Then project the samples onto PC1 and PC2. Then we rotate so that PC1 is horizontal and PC2 is vertical. This just makes it easier to look at. Since these projected points correspond to sample 4, this is where sample 4 goes in our new PCA plot, etc., etc., etc. Double bam! To review, we started with an awkward 3D graph that was kind of hard to read. Then we calculated the principal components. Then, with the eigenvalues for PC1 and PC2, we determined that a 2D graph would still be very informative. Lastly, we used PC1 and very informative. Lastly, we used PC1 and PC2 to draw a two-dimensional graph with the data. If we measured 4 genes per mouse, we would not be able to draw a 4-dimensional graph of the data. Wah wah. But that doesn't stop us from doing the PCA math, which doesn't care if we can draw a picture of it or not, and looking at the scree plot. In this case, PC1 and PC2 account for 90% of the variation, so we can just use those to draw a two-dimensional PCA graph. So we project the samples onto the first 2 PCs. These 2 projected points correspond to sample 2. So sample 2 goes here. Bam! Note, if the scree plot looked like this, where PC3 and PC4 account for a substantial amount of variation, then just using the first 2 PCs would not create a very accurate representation of the data. Wah wah. However, even a noisy PCA plot like this can be used to identify clusters of data. These samples are still more similar to each other than they are to the other samples. Little bam. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, please consider buying 1 or 2 of my original songs. The link to my Bandcamp page is in the lower right corner and in the description below. All right, until next time, quest on. Stat. Quest. Stat. Quest. StatQuest. Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today, we're going to be talking about principal component analysis, or PCA for short. Let's start off with an example of principal component analysis in action. Here's an example PCA plot that I got from an article that I was just reading. It shows clusters of cell types. This graph was drawn from single-cell RNA sequencing data. There were about 10,000 transcribed genes in each cell. And each dot in this graph represents a single cell and its transcription profile. The general idea is that cells with similar transcription profiles should cluster. And we sort of see that in this graph. We see that blood cells form one cluster that's different from pluripotent cells, which is different from neuronal cells, and dermal or epidermal cells. So the big question is, how does transcription from 10,000 genes get compressed into a single dot on a graph? The answer is PCA. PCA is a method for compressing a lot of data into something that captures the essence of the original data. In this stat quest, we're going to learn all about how PCA does this compression. Also, we're going to find out what these access labels refer to. Before we're going to find the nitty-gritty of PCA, we're going to cover a little background material. We're going to have an introduction to dimensions. Just to warn you, this is going to seem very, very simple. But just hang in there. You'll be glad we did this. It'll keep your head from exploding. If you can remember all the way back to first or second grade, you'll remember that one dimension equals a number line. Now, imagine we had a pretend RNA-seq dataset for a single cell. Here, I've labeled the genes just A, B, and C, and the read counts are 10, 0, and 14 for those genes. We can plot these values on the number line. Just like we did in first or second grade, A with 10 reads gets a dot at 10. Gene B with 0 reads gets a dot at 0. And lastly, gene C with 14 reads gets a dot at 14. If we plotted all genes, we might see something like this, a uniform distribution of transcript counts. Or we might get a non-uniform distribution of transcript counts. Some genes might not be transcribed very much, and they'd be on the left side of our number line, and some genes might get transcribed a lot, and they'd be on the right side of our number line. Even though our number line is a very simple graph, we can get some useful information out of it. Now, it's a very a lot, and they distribute. If we plotted all genes, we might see something like this, a uniform distribution of transcript counts. Or we might get a non-uniform distribution of transcript counts. Some genes might not be transcribed very much, and they'd be on the left side of our number line, and some genes might get transcribed a lot, and they'd be on the right side of our number line. Even though our number line is a very simple graph, we can get some useful information out of it. Now, let's fast forward to 5th or 6th grade when we learned about two-dimensional graphs. Now we have two axes instead of just one, and now we can plot data from two different cells instead of just one. Here's a pretend RNA sequencing dataset for two single cells. Just like before, we have the same genes, but now we have read counts for two separate cells. If you can remember from 5th or 6th grade, the way we plot the data for gene A is we go over to 10 for cell 1, and we go up to 8 for cell 2, and we put a point there. For gene B, we go over 0 for cell 1, so we don't move at all, and we go up 2 for cell 2. And for gene C, we go over 14 and up 10. If we plotted all of the genes, we might see something that looks like this. Here, we see that the expression in the two cells is correlated, meaning genes that are highly transcribed in cell 1 are also highly transcribed in cell 2, and genes that are lowly transcribed in cell 1 are also lowly transcribed in cell 2. Or we might see that the expression in the two cells is not correlated, meaning if a gene is highly transcribed in cell 1, that doesn't tell us anything about whether it's highly or lowly transcribed in cell 2. Okay, so maybe sometime when we took calculus, we started drawing three-dimensional graphs. That's just a fancy graph that has depth. With three separate axes, we can now plot data from three separate cells. So now our pretend RNA sequencing dataset has data for three single cells. And just like before, if we wanted to plot the data for gene A, we would go over to 10 for cell 1, up to 8 for cell 2, and then back 8 for cell 3. We then draw lines perpendicular to each axis to figure out where they all meet, and then we put a dot there. I'm not going to do too many examples of this because you get the idea. So this is what we know about dimensions so far. If we have one cell's worth of data, we only need to have a one-dimensional graph, which is just a number line. If we have data from 2 cells, then we need a two-dimensional graph, which is just an XY graph that we learned about in 5th grade. If we have data from 3 cells, then we need a three-dimensional graph. That's a fancy graph with depth. What happens if we have data from 4 separate cells? You guessed it, we need a 4-dimensional graph. The problem is, we can't draw that on paper. And if we had data from 200 individual cells, we'd need a 200-dimensional graph, and there's no way we can draw that. So the question is, are all of those dimensions super important, or are some more important than others? To answer that question, we're going to go back to a data set that just has 2 cells and 2 dimensions. Hypothetically speaking, what if we had 2-cell data that looked like this? Here, we see that almost all of the variation in the data is from left to right. That is to say, cell 1 has some genes that are lowly transcribed and some genes that are highly transcribed. But it looks like all of cell 2 genes are all transcribed at the same level. If we flatten the data, that is, removed the up and down variation, our graph wouldn't look much different from what it looked like before. And if we flatten the data, we could just graph it with a single number line. In this case, we can take two-dimensional data and display it on a one-dimensional graph without too much loss of information. Both graphs say the important variation is left to right. Here's another example of how some dimensions are more important than others: TV and movies. TV and movies are almost always 2D. That is, they're shown on flat screens, at home or in the movie theater, and we don't usually have fancy 3D goggles on when we watch them. So they're 2D, even though the subjects in the movie are 3D. This is okay. The third dimension usually doesn't add that much to the story. This is why, when we cough up the extra $3 or $4 to watch a movie in 3D, we're usually disappointed. Anyways, people look like people, things look like things, even when they have no depth and are flattened on a screen. Basically, a movie camera takes 3D information and flattens it to 2D without too much loss of information. To summarize what we know so far, we know that each cell that we sequence adds another dimension, and we also know that some dimensions are more important than others. So what does all this have to do with PCA? Well, PCA takes a dataset with a lot of dimensions, i.e. lots of cells, and flattens it to just 2 or 3 dimensions so we can look at it. It tries to find a meaningful way to flatten the data by focusing on the things that are different between the cells. We're going to talk a lot more about this later. For any biologists out there, this is sort of like flattening a Z-stack of microscope images to make a single two-dimensional image for publication. So let's start with an example. Again, we'll just start with 2 cells. Here's the data. Like before, the genes are imaginary, so I've just listed them from A to I. And here's a 2D plot from the data from 2 cells. Generally speaking, the dots are spread out along a diagonal line. Another way to think about this is that the maximum variation in the data is between the 2 endpoints of this line. And generally speaking, the dots are also spread out a little above and a little below the first line that we drew. Another way to think about this is that the second largest amount of variation is at the endpoints of this new line that we just drew. If we rotate the whole graph, The two lines that we drew make new x and y axes. This makes the left, right, above, and below variation easier to see. We don't have to tilt our head anymore. And like we saw before, the data varies a lot to the left and the right, and the data varies a little up and down. Note, all of the points can be drawn in terms of left and right and up and down, just like any other 2D graph. That is to say, we don't need another line to describe diagonal variation. We've already captured the two directions we can have variation with these two lines. These two new or rotated axes that describe the variation in the data are principal components. Principal component 1, or PC1, the first principal component, is the axis that spans the most variation in the data. PC2, or principal component number 2, is the axis that spans the second most variation. So these are the general ideas we've covered so far. For each gene, we plotted a point based on how many reads were from each cell. Principal component 1 captures the direction where most of the variation is. Principal component 2 captures the direction of the second most variation. What if we had 3 cells? Just like before, principal component 1 would span the direction of the most variation, and principal component 2 would span the direction of the second most variation. However, since we have another direction we can have variation, we need another principal component. That's principal component number 3. It spans the direction of the third most variation. What if we had 4 cells? Principal 2 would span the direction of 4 with a component for each dimension, or principal the 2. So we know what PC1 and PC2 are, we know what the x and y axes are in this figure. PC1 is the direction of the most variation in gene expression, and PC2 is the second most variation in gene expression. But I bet just right now you're asking yourself this question. This is a plot of cells, not genes. How do we plot cells? So far, all we've talked about is how to plot genes. To answer your question, we're going to go back to the original scatter plot for 2 cells. For now, let's focus on principal component 1. The length and direction of PC1 is mostly determined by the circle genes, the genes on the endpoints, or the extreme genes. Now we're just going to move the graph over to the left side of the screen so we can put other interesting things on the right side. If we wanted to, we could score genes based on how much they influenced principal component number 1. And here's a list of qualitative scores that we might give each gene. Genes close to the ends of the line, like A and F, would have high scores because they highly influence PC1. But genes in the middle, like B and C, would have low scores. We could also use quantitative scores for each gene. So genes with little influence on principal component 1 would get values close to 0, and genes with more influence would get numbers further from 0. Genes on opposite ends of the line would get similarly large numbers, but with different signs. So A might get a positive number, like positive 10, and F, because it's all the way at the other end of the line, might get a negative number, like negative 14. Similarly, we could also rank genes and how they influence principal component number 2. Now we have 2 tables of genes and the influence they have on the principal components. One is for principal component 1, and the other table is for principal component number 2. Now that we have these 2 tables for the first 2 principal components, we can use them to plot cells and not just genes. We do that by combining the read counts for all genes in a cell to get a single value. Here's how to do that. First, we return to the original read counts for each cell. We can then calculate a score for cell 1 by taking the read counts, use them one genes and the component number 2 on the principal components. One is for principal component 1, and the other table is for principal component number 2. Now that we have and the end component might get a negative number, like negative 14. Similarly, you might get a negative and of the lens components like its is mostly determined by the circle genes, the genes on the endpoints, or the extreme genes. Now we're just going to move the graph over to the left side of the screen, and here's a list of quality. Like we could also use quantitative from similarly large numbers, but with different signs. So A might get a positive number, like positive 10, number. Also rank genes and how they influence principal component number 2. Now we have two tables of genes and the influence they have on the principal components. One is for principal component 1, and the other table is for principal first two. Here's how to tell. We can then calculate a score for cell 1 by taking the read count for gene A and multiplying it by gene A's influence on the principal component, and adding that to the read count for gene B multiplied by the influence of gene B, and doing that for all genes. Here's a concrete example. For cell 1, gene A, we have 10 read counts, and the influence gene A has is 10. So the first part of this summation is 10 times 10. The second part of the summation is the read count for gene B, which is point and multiply, and this is PC, same thing as before, except instead of using the weight gene A, gene B, 2, do that for, and in this we've got values for principal component do is principal. What we did there, we did them at each principal component, plot it like we did in similar to cell 1, principal component number 2. Again, we just plot it like we did in 5th grade to cell 1. It would get scores similar to cell 1's. And as a result, when we plotted it on the graph, cell number 3 would be closer to cell number 1 than it would be to cell number 2. Hooray! At long last, we know how they plotted all of the cells on this graph. These are the general ideas we covered so far. Genes with the largest variation between cells will have the most influence on the principal components. That is to say, genes highly expressed in some cells and not expressed in others will have a lot of variation and influence on the principal components. The first principal component captures the most variation in the data. The second principal component captures the second most variation in the data. You can use the original data and the first two principal components to get XY values to plot on a figure. Cells with similar transcription patterns will cluster together. And just like they say on TV, but wait, there's more! We can use the graph to identify key genes. Do you see how cells are spread out left and right, above and below? If we wanted to find out which genes had a big influence in putting dermal cells on the left side of the graph and neural cells on the right side, we could look at the influence scores on principal component number 1. And if we wanted to find out which genes help distinguish blood cells from neural and dermal cells, we could look at the influence scores in principal component number 2. But wait, there's even more? Yes, there's a couple diagnostics you can do if you're drawing your own PCA plot. These are ways you can tell if your PCA is actually worth anything. One diagnostic plot is called a scree plot, where you plot how much variation each principal component can account for. What you want to see in this diagnostic plot is that most of the variation is accounted for by the first two principal components. Lastly, here's a terminology alert. The ways I've been describing things has been fairly intuitive, but there's actually a lot of technical jargon for principal component analysis. The numbers that describe the weights for the importance for each gene to principal component 1, I've just been calling influence, or weights. But in PCA terminology, those weights are called loadings. An array of loadings is called an eigenvector. And that's all there is to PCA. So tune in next time for another exciting stat quest.
So the author's position is that the government intervention and taxation in the free market should be minimized.
I've got a few PCA tips just for you. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to be talking about PCA and I'm going to give you a few practical tips. Specifically, we're going to talk about 1. Scaling your data, 2. Centering your data, and 3. How many principal components you should expect to get. Note, this is a follow-up to my video, Principal Component Analysis, PCA, Step by Step. So make sure you've seen that video first, or at least already know how PCA works. Practical tip number 1. Make sure the variables are on the same scale, and if not, scale them. Here we have math and reading scores for a bunch of students. Let's plot the data. Math scores are from 0 to 100, and they are spread out between 0 and 100 in the graph. In contrast, reading scores are only from 0 to 10, and they are all crammed between 0 and 10 on the graph. If we centered the data and did PCA on it, we'd get this recipe for PC1. To make PC1, mix 0.99 parts math with 0.1 part reading. It suggests that math is 10 times better than reading for capturing variation in aptitude. But this is only because the math scores are on a scale 10 times larger than the scale for reading scores. If we divided the math scores by 10 and replotted, and then centered the data and did PCA on it, we'd get this recipe for PC1. To make PC1, mix 0.7 recipe that 10 times suggests that math with 0.1 part reading. It suggests that math is 10 times better than reading for capturing variation in aptitude. But this is only because the math scores are on a scale 10 times larger than the scale for reading scores. If we divided the math scores by 10 and replotted, and then centered the data and did PCA on it, we'd get this recipe for PC1. To make PC1 mix 0.77 parts math with 0.77 parts reading. This suggests that reading and math are equally good at capturing variation in aptitude. The moral of this story is that you need to make sure the scales for each variable, in this case math and reading scores, are roughly equivalent. Otherwise, you will be biased towards one of them. The standard practice is to divide each variable by its standard deviation. Thus, if a variable has a wide range, it will have a large standard deviation, and dividing by it will scale the values a lot. If a variable has a narrow range, it will have a small standard deviation, and scaling will be minimal. Practical tip number 2. Make sure your data is centered. The very first step, centering the data, is an important one, but not every PCA program does this by default. If you do PCA using SVD without centering, it will still try to fit a line to the data that goes through the origin, and your PCs will not be what you expect. So double check that the PCA program you are using centers the data or center it yourself. Practical tip number 3. How many principal components can you expect to find? In the first example, we had math and reading scores from a bunch of students. We then plotted the data on a two-dimensional graph. We then centered the data, and then we found the best fitting line that goes through the origin. This is PC1. The second PC, PC2, was the line perpendicular to PC1. Then we just moved on without asking if there were any more principal components. So now let's ask the question, is there a third principal component? To find a third PC, we'd need to find a line perpendicular to both PC1 and PC2. And in 2 dimensions, that's not possible, so the answer is no. To see why it's not possible to draw a line perpendicular to both PC1 and PC2, we could add a third line and rotate it until it is perpendicular to PC1 and PC2. This position is perpendicular to PC2, but per sample, i.e. per student, at most we can have 2 principal components. Now imagine that math and reading scores are 100% correlated. Then we centered the data. Then we found the best fitting line, principal component 1. Technically speaking, we could find a line perpendicular to PC1. But if we projected the data onto this line, it would all just go to the origin. This means that the eigenvalue for the new line, the sum of squares of the distances between the points projected onto the line and the origin, would be 0. The data onto this line, it would all just go to the origin. This means that the eigenvalue for the new line, the sum of squares of the distances between the points projected onto the line and the origin, would be 0. This means that PC1 accounts for 100% of the variation, and the new line accounts for 0%. Thus, for all practical purposes, PC1 is the only one that matters. Likewise, if we only had 2 students, and then we centered the data, and then we found the best fitting line, PC1. Then, just like before, we could find a line that is perpendicular to PC1, but the eigenvalue would be 0. So, just like before, there is really only one principal component worth talking about. Another, perhaps simpler way to think about this is that 2 points define a line. So these 2 points can only define a single line. In order to define a plane, something with 2 axes, we need at least 3 points. Now, imagine we had 2 students and 3 test scores, math, reading, and gymnastics. We can center the data, and just like before, since we only have 2 points, and 2 points define a line, we only have one PC. Now imagine we had 3 students. And we remember that 3 points define a plane. And a plane has only 2 axes. Then we would predict that there would only be 2 principal components. So we can center the data, find the line through the origin that fits best, PC1, then find the line perpendicular to PC1 that fits best. And that's it. Since a third line would have an eigenvalue equal to 0, there's no PC3. In summary, technically, there is a PC for each variable in the dataset. However, if there are fewer samples than variables, then the number of samples puts an upper bound on the number of PCs with eigenvalues greater than 0. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more, please subscribe. And if you'd like to support StatQuest, well, consider buying 1 or 2 of my original songs. Okay, until next time, quest on!
What? Still searching YouTube for math help? Are the videos from 2006?
Hey guys, and welcome to another fun and easy machine learning tutorial on Naive Bayes. It's a good day to play golf, or is it? Let's take a look at some of the factors that determine whether or not we play today. These features are weather conditions or outlook, if it's sunny, overcast or rainy. There's also temperature, humidity and wind. Please smash the subscribe button and click the bell icon to join our notification squad. If you think about it intuitively, we are more likely to play when it's not too hot or cold, which means overcast and mild temperatures. If it is less humid with minimal wind speeds, we are more likely to play. If it's too hot or sunny, we may become exhausted very quickly. Let's take a look at our dataset. So if we recorded our circumstances over 14 days, we have our outlook, temperature, humidity, wind speed, and our dependent variable, which is whether or not we play golf. The objective here is to estimate the likelihood of playing golf, yes or no, given weather condition information. So based on this data, let's see how we can approach this problem using the Naive Bayes algorithm. First, we determine how many yeses and how many nos we get from our dataset. So the probability P of C, or probability of our classes, which are yes and no, we can calculate this as follows. So the probability of yes is 9 out of 14. We can count 1, 2, 3, all the way to 9 total yeses from the 14 possible days. And similarly, we can count 5 no's, which gives us a probability of 5 out of 14. Now we also need to calculate the individual probabilities with respect to each features or weather conditions in our dataset. So for sunny, the probability that it is sunny given that it is yes is 2 out of 9. So P sunny given a yes. Why? Because from 9 yeses, it is only sunny twice, as we can see over here. To calculate the probability that it's sunny given a no is 3 out of 5. So from the 5 no play days, only 3 days were sunny. For the overcast outlook, we can do the same for both yes and no classes. We count 4 days that we got a yes and 0 days that we got a no. So the probability that it was overcast given a yes is 4 out of 9. And for not play class, we got 0 out of 5 respectively. Now we can compute these days. No play sunny given a no is 3 out of 5. So from the 5 no play days, only 3 days were sunny. For the overcast outlook, we can do the same for both yes and no classes. We count 4 days that we got a yes and 0 days that we got a no. So the probability that it was overcast given a yes is 4 out of 9. And for not play class, we got 0 out of 5 respectively. Now we can compute these probabilities for all the other features. You can see how easy this is. So assume we need to classify the following new instance, where the outlook is sunny, temperature is cool, humidity is high, and it's a tad bit windy. Should we go out and play some golf, or rather stay indoors and watch a movie? Firstly, we look at the probabilities that we can play the game. So we use our lookup tables to get the probability that outlook is sunny, given play is a yes, is 2 over 9. Probability of temperature equals cool, given play is a yes, which is 3 out of 9. And similarly for humidity and wind, we have 3 out of 9 for both of them. And then we have probability that play is a yes, is 9 out of 14, as we discussed earlier. Next, we consider the fact that we cannot play a game. So for outlook equals sunny, we get 3 out of 5, temperature equals cool, 1 out of 5, humidity 4 out of 5. Wind equals strong, given a no is 3 over 5. And then play equals no is 5 out of 14. Then using those results, you have to multiply the whole lot together. So you multiply all the probabilities for play equals yes, such as the probability that x given play equals yes, multiplied by play equals yes. So that is 2 divided by 9 by 3 over 9 times 3 over 9 times 3 over 9 times 9 over 14. And this gives us 0.053. And this gives us a value that represents the probability of x given a class times probability of a class. Or in this case, we have probability of x given play equals yes times probability that play was a yes. We also have to do the exact same thing for play equals no. So the probability of x given that play equals no times probability that play equals no. That equals 3 divided by 5 times 1 over 5 times 4 over 5 times 3 over 5 times 5 over 14. And this gives us 0.0206. And finally, we have to divide both results by the evidence or probability of x to normalize. The evidence for both equations is the same, and we can find the values we need within the total columns of the lookup table. Therefore, probability of x equals the probability that outlook was sunny times probability of temperature equals cool times probability that humidity is high as well as wind equals strong. As we mentioned earlier. And this gives us our probability of x, which is 0.02186. And then dividing the results by this value, we get the probability that we played golf given x, and this gives us 0.2424, as well as probability that we don't play given an x condition, where we get 0.9421. So given the probabilities, can we play the game or not? To do this, we look at both probabilities and see which one is the highest value, and that is our answer. And therefore, since 0.9421 is greater than 0.2424, the answer is no, we cannot play golf today. Probably you guessed it right. It looks like Bayes' theorem. Bayes' rule. Now, naive Bayes is based on Bayes' theorem, also known as conditional theorem, which you can think of as an evidence theorem or trust theorem. So basically, how much can you trust the evidence that is coming in? And it's a formula that describes how much you should believe the evidence that you are presented with. An example would be a dog barking in the middle of the night. If the dog barks for no good reason, you will become desensitized to it and not go check if anything is wrong. This is known as a false positive. However, if the dog barks only when someone enters your premises, you'll be more likely to act on the alert and trust or rely the evidence from the dog. So Bayes' theorem is a mathematical formula for how much you should trust the evidence. Let's take a deeper look at the formula. We can start off with the prior probability, which describes the degree to which we believe the model accurately describes reality based on all of the prior information. So how probable was our hypothesis before observing the evidence? Here we have the likelihood, which describes how well the model predicts the data. This term over here is the normalizing constant, the constant that makes the posterior density integrate to 1, like we see over here. And finally, the output that we want is the posterior probability, which represents the degree to which we believe a given model accurately describes the situation, given the available data of all our prior information. So how probable is our hypothesis given the observed evidence? So with our example above, we can view the probability that we play golf given it is sunny equals the probability that we play golf given a yes times the probability of it being sunny divided by the probability of a yes. So why naive? Probability theory says if several factors don't depend on each other in any way, the probability of seeing them together is just the product of their probabilities. So in our example earlier, we have the probability that outlook equals sunny given a yes times the probability of temperature equals cool given a yes times the probability that humidity is high given a yes times probability of the wind equals strong given a yes. Or looking at another example, we can assume that sneezing has no impact on whether you are a builder. So the probability of sneezing and being a builder given you got the flu equals the probability of sneezing given you got the flu times the probability that you're a builder given the flu. So the probability of a sneezing builder having flu must depend on the chances of this combination of attributes indicating flu. Looking at the pros and cons of naive Bayes. It is easy and fast to predict a class of its dataset. It also performs well in multi-class predictions. When the assumption of independence holds, a naive Bayes classifier performs better compared to other models like logistic regression and you need less training data. It performs well in the case of categorical input variables compared to numerical variables. For numerical variables, normal distribution is assumed, or a bell curve, which is a strong assumption. Looking at the disadvantages. If categorical variable has a category in a test dataset, which is not observed in the training dataset, then the model will assign a zero probability and will be unable to make a prediction. This is often known as zero frequency. To solve this, we can use the smoothing techniques, and one of the simplest smoothing techniques is called the Laplace estimation. In some cases, like our earlier example, you can just add 1 to avoid the algorithm dividing by 0. On the other side, naive Bayes is also known as a bad estimator, so the probability outputs from the predicted probabilities are not taken too seriously. Another limitation of naive Bayes is the assumption of independent predictors. In real life, it is almost impossible that we get a set of predictors which are completely independent. Naive Bayes can be used for the following applications: for credit scoring for e-learning platforms, medical data classification fused with the naive Bayes approach. It can be used for real-time prediction, so naive Bayes is an eager learning classifier and it is really fast. Thus, it can be used for making predictions in real time. So this algorithm is also well known for multi-class prediction features. We can predict the probability of multiple classes of the target variable. It can be used for text classification, spam filtering, and sentiment analysis. So the naive Bayes classifier mostly used in text classification due to better results in multi-class problems and independence rule, having higher success rate as compared to other algorithms. As a result, it is widely used in spam filtering to identify spam email, and sentiment analysis in social media analysis to identify positive and negative customer sentiments. It is also used for recommendation systems. So the naive Bayes classifier and collaborative filtering together builds a recommendation system that uses machine learning and data mining techniques to filter unforeseen information and predict whether a user would like a given resource or not. Okay, so that is it from me. Please don't forget to like, subscribe and share. Click the bell icon if you'd like to see some